All right, we're going to get into the first module of the Intro to Map Making in R workshop. But first of all, we need to load the packages we're going to use for this workshop. So these packages include spatial data, tidyverse, anything with shape files, making rasters, static maps, interactive maps, map data, tmap insets, as well as saving the interactive maps. We're not going to use all of them for this first module, but we'll just load them here in one chunk. Might take a moment to run. There we go. So this first module is importing, exporting, projecting, and cropping spatial data. So this is the first module of the Intro to Map Making workshop series. Essentially, you can load any type of spatial data into R. And by spatial data, I mean the data that contains some sort of location information like state, county, country, city, lat, long, and the attributes or characteristics of those locations. There are many types of spatial data, and some of the most common types, and the ones you're going to find most readily, are vector data, such as points, which are like an X and Y coordinate, so lat and long, lines, ordered points, the shapes of linear features like streams or rivers, polygons, which are closed loops of lines. So the points, lines, and polygons all build off of each other. This would be like outlines of states or countries. Raster data, which are pixel-based data where each pixel has a value of something, like a digital elevation model, satellite imagery, or land use maps. And then attribute data, which are characteristics associated with the vector and raster data, like the state name, type of land use, type of agriculture, species, habitat, etc. So those are the three things we're going to be working with. Raster data to a very limited extent because this computer I'm working on doesn't have much RAM and it takes a lot more processing power in R to use raster data. All right, first thing we need to do is be able to import our data. So importing spatial data is really simple in R. CSVs that contain spatial data like lat, long, UTM coordinates, something like that, can be imported like a regular CSV file using read.csv or read_CSV. You import shapefiles, which are the .shp extension, like which are the vector data, points, lines, and polygons using read_sf. And you import rasters with the raster function if you have a .tiff or another type of raster file. So first we're going to read in this fish data set. And these were introduced in the intro to this workshop series, but as a reminder, this is the same data that was in the dplyr data wrangling data visualization workshop series, and it is community fish data from the long-term resource monitoring element of the Upper Mississippi River Restoration Program, and it contains lat and long of different fish that were collected in different habitats during electrofishing and other sampling events. So we have things like lat and long as UTM coordinates here. This states data set are just the states and territories of the United States. This raster data set is USDA or United States Department of Ag crop data. For those unfamiliar with saving data sets in R, what we're doing is using the reading function to bring in the data, the appropriate one for the data type. So since this fish community is a .csv, we're using read_CSV, saving it using this arrow designation as an object named fish. For the shapefile, .shp extension. We're reading it through read_sf and naming it states. For the raster, we use the raster function. It is a .tif file, .tif. We're saving it as the name crop. So when we pull up something like crop or fish or whatever, and we can just run the name fish, it's going to show us what that data set looks like for those unfamiliar with reading in objects. You'll notice that these shapefiles and rasters, especially very large ones, can take a while to read into the R environment. So just be a bit patient with reading in really large data sets. But it is still faster than reading these files into ArcMap on a basic computer. So before you work towards using the data sets to make maps, you should always view the data to make sure it was imported correctly and you understand its structure. So these are a few of the different viewing functions for data sets. Names gives you the column names of the data set. This is great for CSVs, which we're using a fish data set here, which is a CSV file. We've got the names of the columns here. Head gives the first 6 rows of data. So we have the first 6 rows and the column names. Tail is the last 6 rows if you wanted to look at the top and bottom of your data set. str gives the structure of your data. So what this looks like is it has the column names. It has the type of data you have, which is a special table. It's got the rows and columns. And for each column name here, it's got the type of variable it is. So stratum here is a character, and it'll show you what some of those columns are, rows are in that column. Sdate here is a character. Stime is an hour, minute, second, or time variable, and so forth. Glimpse is basically the same thing as structure, but it's a tidyverse function, and I think it looks a little bit nicer than structure. Everything's a little bit more lined up. So we've got just the rows and columns here. We have our columns. We have the type of column, character, time, and we have some of our values here. It's just a little bit more lined up and a bit cleaner than the str function. For shapefiles, I only recommend these 2 functions to really look at them. Names will give you the column names in the data set still. Object ID, region, division, state FP, state NS, etc., and glimpse. These are all the columns in your states shapefile, object ID, region, etc. What those data types are, integer, character, and then those values in each column. For rasters, really the only function that works here is glimpse out of the ones I've suggested. And what we can see is that it's a formal class raster layer with 13 slots. So taking a step back a moment, when we look at the fish data set, for example, a CSV or a states file, we've got this $sign here, and it's saying this is a column. Because when we look at regular CSVs or the shape files, you call parts of the data using the columns. So if we were to put that in a function or something, let's just do unique, which is looking at the different factors in a column. And within our fish data set, we're going to look at the stratum column. You call that specific column using this $sign. And then we can say these are the different stratums in the data set, for example. Can do the same thing with these states shapefile. The $sign is going to get at those different columns. Division is 0 through 9 here. However, with the raster data, and we see through the crop, or the glimpse of the crop data set, we have this at instead of a $sign. These slots refer to these different at symbols. So we have the file, we have the data, we have the legend, title, ncols, nrows, CRS, which is a projection, etc. You have to get at the at information to like look at anything in here. So if we wanted to look at the data, it's glimpse crop, which is the name of the raster, at data, which is this second at here. We can see what that looks like. All right, this is likely our attribute table. We have values, min, max, band, that kind of information here, which should, if you're familiar with rasters and using them, that's the information you need. And if you want to get at the attributes, it's within the at data with another at attribute. So to look at that, it's glimpse, crop, at data, at attributes. We have ID, class names, and histogram here within our attributes. So the difference between rasters and all other data basically is that other data have the $sign to get at columns, and rasters you have the at, and you have an at again. But now we have the $sign to get at the specific columns here, because these are the actual data columns. So we have $sign for the data columns. So just as a way to look at that, some sort of nuance that is not very familiar with people or to many people. So that looks at different viewing functions for the data. So finally, to make sure our data imported, we may want to do a quick visualization of those data. I will say that this is the only time we will use in this workshop series to using a base R plotting function to quick plot the data. I really only use base R plots for quality checks of the data. So I would do a quick plot of a shapefile or raster to visualize it. Notice the following code takes a bit of time to run, and that's because there's a ton of data in the files that R has to process before it can plot. So if we plot this crop data set, it's going to give us a little spinny wheel until it makes a plot, if it will make a plot. But to do a quick plot in base R, it's just plot, and then you put the name of your raster in there. And this is what that data looks like. So these are all the crop data. We've got 0 to 250, and we have different colors for our crops. And then if we were to plot a shapefile, it says plots states. It's going to take a moment to run. This is a shapefile, and we should get the states and territories of the US. And basically what it does is it plots all of the different variables and some of them have different colors and stuff, but we can see it's plotting the outline of the United States and its territories. So this works. Looks like the data were entered correctly, essentially, that we were able to produce a raster that looks like a outline of the US and has different colors, and then the outline of the US states and territories using the shapefile. All right, so that's importing the data and viewing it. We're going to look at the spatial data information contained in some of these data sets and what we need to use with them. So you'll want to know general information about your spatial data, like what projection and what datum are being used. These data are stored in shapefiles and rasters, usually, or they should hopefully be accessible in the metadata to know which one it is if they're unprojected when you bring them in. So as a quick reminder about projections, this is from Google AI. A spatial data projection is a mathematical calculation used to transform a 3D geographic data into a 2D plane. So it's stretching the like globe essentially in a certain way. It's flattening the Earth's curved surface to display it on a map. And all maps are not correct to the globe of the Earth because they involve squishing things, especially the poles or the equator. But it involves converting spherical coordinates like latitude and longitude into planar coordinates on a flat surface. which is distorted in some way or another. Some of these common projections are like WGS84 or NAD87. That what's important to know with these projections is that for some packages, all your data that you're putting in one map or you're analyzing together have to be in the same projection. For other functions, like within the tmap package, it actually, as long as your data are projected already in the correct projection, that it will convert all of your data to the projection that is uniform for it. But other packages like ggplot, leaflet, or spplot will not automatically convert to the same projection. So we're going to briefly cover projecting and reprojecting data. One, we'll need to assign coordinate reference systems to lat-long data in a CSV to make it spatial. This is very, very common that if you just have lat-long data or UTM data, for example, it's not already assigned a coordinate reference system or CRS or projection. So it's unprojected, does not have a datum, and you will need to assign it one to be able to map it. And that will also convert it to a spatial data frame, essentially. And if we intend to crop rasters to a specific extent before mapping, the spatial data need to be to have the same projection because you have to crop raster or shapefile or anything. The thing you are cropping it to needs to be in the same projection as that other data. So first, we're going to look at the information stored in the data regarding coordinate reference system or CRS and the extents of the data set. So this st underscore geometry underscore type on our states data frame tells us the geometry of our data. This is a multi-polygon. Every component of this data set is a multi-polygon, which makes sense. It is the states and territories. Those are made of polygons. The st underscore CRS gets at the coordinate reference system. Our coordinate reference system is a popular visualization CRS Mercator. That is the projection CRS. The GeoCRS is WGS84 or World Geodetic System 1984. That is the datum here. So this is something that actually has the CRS in here for us to use just as like, this is the information. This is one of the most common ones, the WGS84 here. ST underscore B box is the bounding box of the data set. These are the minimum and maximum longitude and latitude, or whatever projection it's in. It might be UTM coordinates. It could be like meters or anything like that. And this is how to get the CRS of a raster as well. It's the same function, st underscore CRS. We're just putting in the crop raster instead of the states. And we'll notice here we've got this proj4 string. It doesn't have a proj CRS here. It has the datum. It's a North American datum 1983 or NAD83, which was the other common one I cited. This is the user input datum is NAD 1983 here, units, meters. All this information is important for what we're going to be doing. First, we're going to take the CSV file of the fish data set. We did not look at it within these functions because it is unprojected data. It's just a CSV that has lat and long. This is a really common way of storing spatial information is just lat and long in a CSV file. These data contain, again, fish collections and the lat and long for those fish collections, but this data set is not a shape file. It has the spatial data, but we cannot map it yet, and we will need to convert it to a shape file in order to map it. If we need to make a regular data set, like a regular CSV that contains coordinates, a spatial data set in R, we need to know its coordinate reference system. and project the data using the CRS using what is called a proj4 string, which I mentioned. This crop data set. This is the proj4 string, projection string. For your own data, you'll need to identify the coordinate variables. It might be x, y, latitude, longitude, easting, northing, etc., whatever the coordinate variables are in your data set. And you need to know what projection it's in. All right, if we look at our data set, we can use this st_geometry type, and it gives us an error because it's not some sort of spatial data already. It's just a CSV that was read in. But if we look at our data set, we have this UTM East, UTM North, Zone 15E, Zone 15 North. So if we look at that more thoroughly, they're the same thing, but this is just based on Zone 15 only, while this will vary if it's in different zones. So if we look at our UTM zones, unique fish, our UTM zone here, right, this function or this column, we have an NA in here, but we have 15 and 16 in different zones, which are going to mean different projections potentially. So we're just going to filter for one of these zones, which is 15, just to make this a little bit more simplistic. So we're going to write over our fish data set, and we'll get into this in the second module of this. But if you looked at the dplyr or tidyverse data wrangling tutorials, you'll know how to do this. We're just filtering for zone 15, but we'll look at that a little bit. So we have our data set. We now have it filtered to just one UTM zone for simplicity for our purposes here. How do we know what projection or coordinate reference system we need for these data? Well, hopefully the metadata has that information in it, or there's information in the CSV itself to tell us what reference system it is. This data set has the UTM zone information provided. So this clues us into our coordinate reference system, or CRS, because it has a UTM zone and we can access the metadata for this data set. I know it's in NAD 1983. And then we can use this spatial reference website to look up our proj4 string. This website is very helpful to know what is going on. You can look up stuff in here. We've got Esri references, SPSG references, and a few other ones that you can look up what the proj4 strings are. .prj here. And I guess it'll save it. You can also look at it in a few other ways. But if you need to know your proj4 string, you can look, and you don't have one in your data set, you can look at it through this website. I looked this up before, but the proj4 string from this website for NAD 1983 is this. Proj equals UTM, zone equals 15, because we filtered for the 15 here, and all this information. So we can say this proj4 is an object and use it to project the CSV data frame into a spatial points data frame. So we're going to say this as object fish CRS for coordinate reference system. It's the function CRS, coordinate reference system, with, in quotation marks, puts that proj4 string from the website right there. To convert a CSV into a shapefile, it's this function st_as_sf. Specify the data set that was unprojected, our fish CSV file. Specify within the data set what our coordinate columns are. We're going to use UTM East, UTM North. We could also do this one, but we're just going to pick these two. So we have UTM East. The east is the x-axis, that must be first. UTM north, y-axis, second. This is within the concatenate function for the coordinates because there are multiple coordinates here. Use this C to bind them together. And then state the CRS, which we saved as object fish CRS here. So CRS, coordinate reference system, equals what's stored in this object. So if we run this, oh, I did not run that first code. All right, now we can look at the class and some other data with the fish locations here. Class SF for spatial data. Head. So we've got, it looks pretty much the same. It's class SF now, so it's spatial. We do not have UTM North, UTM East in here, but we still have these ones because we didn't use them. Whatever columns you're using for your coordinates will not be in your data after this. It's using them as coordinates instead, so it's not in the data anymore. Glimpse pretty much looks the same minus those two other variables. Structure, same. We've got it as an SF object here rather than a CSV. And if we plot it now, we actually get these spatial points plotted for different variables here. So these are the points in a coordinate reference system plotted down. It's a very simple process using this st underscore as underscore sf to make any CSV into a projected data spatial points data frame now, or SF. So now we've created a spatial points data set from a CSV. We can convert any XY coordinates in a CSV to spatial points data frame if we know the coordinate reference system or projection needed. Okay, next we're going to convert some USA cities data into a spatial points data frame as well. It's something we'll be using in the future. This is in the maps package in our US cities. What this looks like is just the names of the cities, which state it's in, the population, the lat, long, the capital. It's information here. So we can look at it just to make sure we understand what it looks like. It's a data frame. It's not an SF object or anything like that. This was from the one spatial points reference or spatial reference website for the CRS of WGS 84 that is in long lat because these data have long and lat. And if you look at the information in the help file for this data series, it is WGS 84. So this information was available for that. We're going to make it a spatial points data frame, right, and name it USA city locations. So again, this is the function st underscore as underscore sf, the name of our unprojected or uncoordinated data set, US cities. Our coordinates now are long and lat. Long is the x, lat is y, and our CRS here is what we saved as PRJ right there. So if we run that, we now have this as a spatial points data frame and we can plot it. So those are all of our cities based on long lat in the US. So in all cities, it's some sort of threshold, but let's see what that looks like. Okay, that's how you convert CSVs that have a coordinate reference, like a lat long UTM coordinates or whatever in them, to spatial points data frames that you can then use to map. Next, we're going to reproject spatial data into a different projection. Again, I mentioned that if you have to crop data or if you're mapping it in different packages, all of your data that you're mapping onto one map and for cropping need to be in the same projection. NAD 83, WGS 84, etc. And if you need to reproject your data to a different projection, you can do it easily using the st underscore transform function. So let's say we're going to crop like our fish locations to our states or something like that. So they need to be in the same projection. And they're not. This USA cities is WGS 84, and this one is a UTM coordinate for the fish. So they are different here. So we've got UTM coordinates with a zone, and we have long lat WGS 84 there. What we're going to do is st underscore transform. We are transforming here. Our x is fish locations, our projected fish location information. And we are transforming it to this CRS. We're going to use st underscore CRS because that gets us the CRS of whatever is in here. It's going to use this CRS that's of the US city locations to reproject the fish locations into that coordinate system of this other data set. This is a really easy way to just transform them to the same data set. You could put the proj4 string in here that we use to project the US city locations as well, which was saved here. Or you can just say, do the CRS of this data set. Either one will work, it'll give us the same thing. So if we do that and we look at fish locations 2, it's now in the WGS 84 projection. It's no longer UTM, easting, northing. So we successfully reprojected into that WGS 84. So that's a really quick and easy way to reproject data. Now we could then crop these data or do anything with them. So if we need to crop spatial data, for example, we only want cities in Missouri from the USA cities data set. There are multiple ways to crop a spatial data set. If we look at the cities data set here, we've got the name of the city, we've got country, etc. is the state here, population, capital, etc. So lucky for us, if we just want to get Missouri, we could filter this data set, which we're going to get to in the second module of this. But we could do this really easy, just saying, take the city's data set and filter where the country.ect, the state equals Missouri. And that's just going to give us the Missouri cities, which is really nice, very easy to do. We just have cities in Missouri now. That's it. So that's really easy, but what if you don't have something like that, or you're cropping to a different extent that's not in the data set? Maybe you want to crop to a county or something that's not in there. Or that just those data aren't available for us to our extent. So instead, we need to crop the data based on another set of data that has the extent we are interested in. For example, the Missouri state polygon from the state's data set or something. So we're going to crop the state's data set to the Missouri polygon. So this is just giving us Missouri, the outline of Missouri. That's what Missouri looks like. We know this data set is in the WGS 84 projection. So here's our proj4 string for these states data, and we're just going to transform the states data into, transform the Missouri data set for the state outline into WGS 84 projection, which is what we need to transform or to crop the cities, which was also in the WGS 84 projection. So if we look at our states data set a minute, STCRS, Missouri, that is in WGS 84 already, but if you needed it to be in WGS 84 and it was not, this is the same thing we just did where we're transforming it to a different projection. So transform the Missouri using this CRS or using the ST underscore CRS of our USA city locations. Same exact thing it's going to do. We'll just run it just to do it. And then we use function stcrop. St underscore crop. They're all st underscore something here. Makes it a lot easier to remember. We're cropping our city locations that contain all the cities in the United States to our Missouri shape outline that is in the same projection as our city locations data. And this is going to give us the Missouri cities within that outline. So we're going to look at the data here. If we look at the data, we should only see Missouri here. But we don't. We also see Illinois, Arkansas, Kansas. So what's going on when we use this crop function? Why are we getting other states? Why aren't we just getting things cropped to the Missouri outline? It's because it uses the bounding box of the outline. So if we plot Missouri again, it's using the bounding box. So what it's doing is taking the maximum and minimum latitude, so north and south, and see how it goes down a bit. And then the maximum minimum longitude, so anything that goes over from the top of Missouri there and the bottom of Missouri down here. So it's going to use the full extent, that bounding box for crop. So that's not what we want with this. We actually just want it to the shape of Missouri. So what we can use instead, if we want it just to the shape rather than the bounding box, that is ST intersection. And it's the same thing as ST crop, it's just going to do it to the bounding box. So we have USA city locations, and then crop it to the Missouri transform, or the Missouri state outline. And now we have our Missouri cities we can look at, and they are all just Missouri now. It cropped it to just Missouri outline. So it looks a little bit different than our original one. So now we only have cities from Missouri in the dataset using ST intersection. Here, this is going to crop raster data. Not getting too much into this because many rasters are very large and not actually what we need for mapping. We can crop them to the extents that we do need. So we will not be discussing transforming, aggregating, multiband versus single band rasters, etc. This is just like for your information if you need to use a raster for something, but just note that it may or may not run on your computer. So if you want a crash course on raster math or anything that is more raster related, if that's applicable to you, check out Dr. Emily Birchfield's website that has more information on rasters. So we're just going to briefly cover cropping raster to add to a map. The easiest way to crop raster data is to an extent of another shapefile or of a known extent like a bounding box. However, these don't actually look very good for creating maps as the raster won't be cropped to the shape of the shapefile, just like using stcrop here, that was to the bounding box rather than st intersection, the actual shape. So what we're going to do is we're just going to use the Missouri shape outline. We're going to plot that a second. Just the outline of Missouri again, same thing that we were using. We're going to get the coordinate reference system of our crop data set for our raster. This is the proj for string, all those little plus signs and equal signs. That's what's going in here. That is our CRS for our raster data. We're saving that as CRS now. We will need to transform whatever we are cropping into the same projection as the raster. You could also reproject the raster. That is going to take much longer, and then you have to deal with aggregating your raster values during reprojection. We are not focusing on that. We are going to do the easier route and reproject the shape file to crop to. So again, this is the st transform function. We are transforming the Missouri shapefile, which is currently in WGS84, to this CRS, which is saved here. That is the CRS of the crop data. And we could just put CRS here, or we could say CRS equals ST CRS of the crop data. Same exact thing will happen. So now if we look at the transformed Missouri, it's in NAD 1983. It is the same projection now as the crop data. So now that the two data sets have the same projection, we can use the crop function in the raster package, which is just crop, not st underscore crop this time. This is for cropping rasters specifically. For cropping the crop data set, I should name this something different. So put your raster you are cropping first, and then what you are cropping to the extent to, which is our Missouri transform. Cropped crop extent here. It's going to take a moment to crop it, and then we can plot the cropped raster, assuming it will crop it in a convenient time frame. All right, now it's done cropping it. We are going to plot it. So just using a quick base R plot our cropped raster. And this no longer looks like the United States outline. It is a bounding box of Missouri that has the crop extent. I'm familiar with this area, so I can see where there's like a weird line here, and that is the Mississippi River going through. There are no crops within the Mississippi River. This other line going through Missouri is the Missouri River. So I know it is cropped to Missouri. It's bounding box. So again, this gives our bounding box. It does not give us the shape of Missouri. To do the shape rather than the extent or bounding box, it takes a different function. It's not crop, it is mask. So here we're going to specify it's in the raster package through : mask function. We're just going to crop our crop data already so it like takes less time to run. But basically you just say mask, the raster you're trying to crop, and our mask equals whatever other data we have that's in the same projection as the raster. So that was our Missouri transform data. Basically looks the same as here, but instead of X and Y in the crop function, it is mask, the data set you are cropping, and then our mask equals. And we're going to say this as crop shape. So it's going to take a moment to run. And now that is finished running, we can plot this cropped shape. Give it a moment. So what this looks like now is the outline of Missouri and not just the bounding box. So using that mask function, we go from this extent all the way to just the outline of Missouri. That mask function, this is more likely what you will want to do is to use that mask function, or for a shapefile to use the st-intersect. So we had done this by reprojecting the shape file to the same projection as the raster. Do not run the following code. But if you need to reproject a raster, you can use the function project raster from this example below. You will need to pay, however, special attention and know what you are doing to the data types of your raster cells when selecting a method. And note that reprojecting a raster takes so much longer than reprojecting other spatial data, but there are instances where you should definitely do it. So we're not going to run this code, but it is here for your reference. Project raster, the name of your raster you are projecting, your resolution that you are reprojecting to. Here we're just doing the same resolution as the original crop data set. So our res is the crop data set. The CRS or coordinate reference system you need to project to, which this put a prosh forcing string in there, put some other function in there. And then your method, this is nearest neighbor, which is used for categorical data. You can do bilinear for numerical raster data. While we have numbers here, these numbers refer to a crop type, which is actually categorical and not a number. We're not running this again because it's going to take way too long. But if you do need to ever reproject a raster, this is the way to do it. So finally, in this module is exporting a shapefile. So now we know how to import them, project them, reproject them, crop them, mask them, etc., and look at the information contained in them. So now we want to export anything we have created, because then we don't have to run it again. We have our new filtered dataset, our mask dataset, etc. So just like we can import them, we can also export the ones we created. So we're going to export our fish locations in Missouri City shapefiles that we changed from CSVs to shapefiles for safekeeping, as well as the Missouri shaped crop raster. So to write a shapefile, it is st_write. Going to the same functions as the st once again. Here, st_write our fish locations to. That was what we had saved our projected fish data as. This is the name you are saving it as in the file path. So within the folder that this R Markdown document is saved in, we're going within the data folder, we're going within the exports folder, and we are saving this as ltrm fish locations wgs84.shape. All of that in quotation marks. And then like what type of driver you have. This is an Esri shapefile we're saving it as. It's just a common type of shapefile. To save a raster, it's write raster. It's capital R. The name of our raster we're saving, which is the crop shape, the Missouri raster. Again, our file path, data exports, the name of our data set we were saving, Missouri crops raster, and with the file extension .tiff. Or you can save it to whatever other file extension you want. That's a raster. I prefer .tiffs. And then again, st_write for our Missouri cities shapefile. Again, our file path name and what we're saving it as cities in Missouri.shape. And again, driver is Esri shapefile. So all these are going to save it. If you were in this full day workshop or anything else, this now finalizes the first module of importing, exporting, projecting, cropping, viewing data, spatial data specifically. And this would be the break to now look at the exercise one, which ties directly to the information here using different data sets. So now taking a break for these exercises, and you can work on them if you want to practice this information yourself.